All right, so what we're going to look at in this video are some common things that you should know about interpreting mass spectra. And then in the video that follows, we'll look at common fragmentation patterns of various functional groups. So here's kind of a simplified mass spectrum of the compound pentane. So I'll draw its skeleton formula there. And the way that these spectra are plotted is you have intensity or relative abundance on the y-axis. This is a measure, a relative measure of the prevalence of that particular ion. The higher it is, the more of that ion is present. And it's plotted on the x-axis versus mass. So this m over z is mass over charge, and the charge is usually like 1. So, that's why we just refer to the x-axis as the mass of that particular fragment. Now, there's two typically important peaks. Not that the other ones don't matter, but these are the ones that we typically look at first. And then we'll look at some of the more other prevalent peaks if it's important. But the ones that you should be able to recognize off the bat is the base peak. The base peak is the peak with the highest abundance. So in the case of this particular spectra, that's this one here at 43. Now, don't mix this up with the peak that has the highest mass value. Okay. Sometimes that's the base peak, sometimes it's not. Sometimes what we say the molecular ion is. Sometimes it is, but very often it's not the base peak. In general, you find the base peak by finding the signal, finding the peak that has the highest abundance. The other important one that you should be able to find is what we call the molecular ion. This is the peak with the highest mass. And that is usually 99% of the time the molar mass of your compound. So if you were to take the molar mass of pentane, it would be 72. So what that 72 represents is the molecular ion. When an electron is fired at pentane, it dislodges an electron, so it becomes a radical, and then a cation as well because it lost an electron. Now, what happens is that cation, that radical cation, will fragment because it's not very stable, and it will give off a cation and a methyl radical. Now, what is the mass of this um, cation, or I'm sorry, radical here? Well, if carbon's 12, you got 3 hydrogens, that's a mass of 15. Look at this here. If I go from 72 to 57, what is that a change in? Well, that's a change in a mass of 15. So what 57 represents is the loss of a methyl carbon from the molecular ion. And so it's a pretty good bet that this 57 represents that butyl cation. And so if I keep on doing this, if I go from 57 to 43, what is that the difference of? Well, that's a loss of a mass of 14. So if that butyl cation loses another carbon, we get this cation and a CH2 radical. Okay, well, CH2 has a mass of 14. So we could say that that 43, that our base peak represents that fragment. And we'll kind of get a little bit more into slightly more difficult examples. Alkanes are very easy because a lot of times you're just lopping off a carbon on the end, and then you get the next lowest peak. And so you can kind of see like, oh, I'm not really caring about, some of these smaller ones. I'm just really focused on the largest fragments. Now, generally, the molecular ion is usually even, but if it's odd, then what that means is you have an odd number of nitrogens present. That's kind of one of these, sometimes that's a useful thing, sometimes it's not. But if you think you have a nitrogen in your compound, then the mass spec would show an odd molecular ion for if you had an odd number of nitrogens. So if you had one nitrogen or three or five, the molecular ion would be an odd number. Now, sometimes you will see a very small peak above the molecular ion. So peaks above the molecular ion indicate isotopes. So for example, in this compound here, I want you to look at the molecular ion. Okay, so notice it's actually kind of small here, right there at 142. And you kind of see this little blip right there. So that's this blown up here. So this is our molecular ion. That's the molar mass of the compound. But why are we seeing this, what we call an M+1 peak here? And that is due, so if you have that very small M+1 peak, like that's like about 1% of the height, that is due to there being carbon 13 present in the compound. So I don't know if this is talked about in general chemistry, but when it comes to carbon isotopes, like 98 point some odd percent of all carbon is carbon 12, and like another 1% is carbon 13. So it's a pretty good bet that when you inject up like millions and millions of molecules into a mass spec, that at least 1% of those carbons somewhere in those molecules are going to be carbon 13. So sometimes you see that M+1 peak. But this really isn't useful since all organic molecules have carbon in it. I mean, that's why we're taking this class. But I bring this up because there are a few instances where those peaks past the molecular ion are useful for identifying certain atoms. And where we will see this is with chlorine and bromine. So nearly 25% of all chlorine atoms is um, chlorine 37, and the rest is chlorine 35. So the ratio of chlorine 37 to chlorine 35 is 1 to 3. And so if you look at your molecular ion and then you see 2 units away another peak that's about a third of the height. So here's our molecular ion here. And 2 units away at 114, there's what we call an M+2 peak. And that M+2 peak is 1/3 the height of the M plus peak. And what that basically tells you is that chlorine is present in your molecule. Now we could do something very similar with bromine. Because bromine, the ratio of the two isotopes of bromine of 81 Br to 79 Br is about 1 to 1. And so since half the bromine atoms that exist are bromine 81 and the other half are bromine 79, if the M+2 peak, so here's our molecular ion, and then there's an M+2 peak that's nearly equal in height, that is a ratio of 1 to 1, then that tells you bromine is present in your unknown. Now, there are some other isotopes that kind of do this, but it's not super common. So I'm not going to go over it. And again, as I said earlier, um, having an M+1 peak representing carbon-13, not really useful. You can kind of ignore that. But if you're looking at an unknown substance and you see an M+2 peak, I'm gonna emphasize it, an M+2 peak that's 1/3 of the height, that tells you that there's a chlorine there. And if that M+2 peak is nearly equal to the height of the molecular ion, then that tells you you have a bromine present. And so in the following video, we're going to be looking at common fragmentation patterns of a lot of the different functional groups.